In this lesson, we're going to look at more examples of partial differentiation. In our first example, we're going to look at a situation where we have a plane at x equals 1 that intersects the paraboloid z equals x squared plus y squared, and the intersection forms a parabola. We want to find the slope of a tangent line to the parabola at the point 1, 2, 5. So let's start by drawing our z-axis. So here's our z-axis, it's a positive z-axis. And here's our y-axis. And this is 3 dimensions. So here we have our x-axis, and you sort of imagine that this is corner here, 3 dimensions. And we will draw the graph of z, this graph here, which is the z equals x squared plus y squared. Now that's going to form a paraboloid here like this. Let's draw that. Here's our parabola. So that's our paraboloid that's coming from this equation. And then we have our plane at x equals 1, and we'll draw that in red. So here's x equals 1, so we have a plane that goes through that. So here's a sort of a cutout of that plane, and it's going to come through here. And of course, this is sort of a section of the plane that's going to sort of cut through here. It's supposed to be straight, a little curve there. Okay. And so it's cutting through a section, and what we're looking for is a tangent line at the point 1, 2, 5. So something like a line that's going to come through and be tangent, like that. So here's our point right here, 1, 2, 5. So what we're going to do here is we're going to take the partial derivative of z with respect to y at the point 1, 2. And I'm going to move this up here. Okay, so that's going to be the partial derivative with respect to y of x squared plus y squared at the point 1, 2. And we'll move that one up too. And that's going to give us 2y, because this is with respect to y, so the partial derivative, of course, of x squared, well, x is a constant, so that's going to be 0, and the partial derivative of of y squared is 2y, and that's evaluated at the point 1, 2, which is going to give us 2 times y, and y is 2. So that's going to give us 4. So the slope of this tangent line is 4. I'm going to put a box around that answer. And there we have it, the slope of this tangent line right here. And that's a line, so let's give it some arrows at the end. And the slope of this line is 4. In this next example, we're looking at x, y, and z, which are independent variables, and a function of x, y, and z, which is equal to x times the sine of the binomial y plus 3z. Here, we're going to find the partial derivative of f with respect to z. So to do this, we're going to find the partial derivative with respect to z of f, and f is x times the sine y plus 3z and when we do this, we're going to factor out the x because we treat x like a constant, and so we're going to take the partial derivative with respect to z of the sine of y plus 3z, and I'm going to move that up. I guess that came up in pieces here. That's strange. Let's move that over. Y. Move that I over. That somehow came apart. Okay. All right. So what we're going to have is we have the x and the partial derivative of the sine. Well, the derivative of the sine is the cosine. So the derivative of the sine of x plus 3z is the cosine, I'm saying y plus 3z, of y. We have to chain rule that by multiplying this by the derivative of y plus 3z with respect to z. So the y is considered a constant, so that's 0. The derivative of 3z with respect to z is 3. And what we want to do is move that 3 to the front, and our answer is 3 times x times the cosine of y plus 3z. And I'm going to put a box around that. So this is the answer. This is the partial derivative of our function f with respect to z. In our next example, we're working with resistors. If resistors of R1, R2, and R3 measured in ohms are connected in parallel to make an R ohm resistor, the value of R can be found from the equation 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Find the value of the partial derivative of R with respect to R2 when R1 equals 30, R2 equals 45, and R3 equals 90 ohms. So I'm going to rewrite that equation with exponents. So R to the negative 1 is equal to R1 to the negative 1 plus 2 to the negative 1 plus R3 to the negative 1. So if we take the partial derivative of the left-hand side, that is of R to the negative 1, with respect to R2, we do that to the left-hand side, then we need to take the partial derivative with respect to R2 of the right-hand side. That is R sub 1 to the negative 1 plus R sub 2 to the negative 1 plus R sub 3 to the negative 1. Now on the left-hand side, we have to keep in mind that R is a function of R2. So we have to use a chain rule here. So first we have to take the derivative of R to the negative 1 with respect to R times the derivative of R with respect to R2. That's the chain rule. And on the right-hand side, when we take the derivative of r sub 1 to the negative 1 with respect to r2, well, this is a constant, so that's going to give us a 0. And when we take the derivative of r sub 2 to the negative 1, we're going to have a negative r sub 2 to the negative 2. And then the last one is we take the derivative of r sub 3 to the negative 1. Well, that's a constant, so that's also going to give us a 0. Now going back to the left-hand side, when we take the derivative of r to the negative 1 with respect to r, we're going to get a negative r to the negative 2. And that's going to be multiplied by the partial derivative of r with respect to r sub 2. And I just realized I forgot the partial derivative sign there. And that's going to be equal to, well, let's rewrite this, a negative 1 over, instead of writing to the negative 2, we'll say r sub 2 squared. And so now I'm going to take this and sort of come over here. And let's rewrite that left-hand side. That's actually a negative 1 over r squared times the partial derivative of r with respect to r sub 2, and that is equal to a negative 1 over r sub 2 squared. And so I'm going to multiply both the sides, the left and the right, by a negative r sub 2 over 1. So then we have, that's times a negative 1 over r squared times the partial derivative of r with respect to the partial derivative of r sub 2. And on this side, I'm also multiplying it by a negative r squared over 1. And that's times a negative 1 over r sub 2 squared. And of course I did that so that I could cancel these out. And I end up with the partial derivative of r with respect to r2 is equal to a positive r sub 2 divided by, a positive r squared divided by r sub 2 squared. Okay, and I'm evaluating that at a point where r sub 1 is 30, well, we lost r sub 1. R sub 2 is 45. And so let's go ahead and what we're going to need to do is we need to find r. And then we need to find r sub 2. So to find r, well, we know that 1 over r is equal to 1 over r sub 1, and r sub 1 is 30, plus 1 over r sub 2, and r sub 2 is 45, plus 1 over r sub 3, and r sub 3 is 90. And if we look at these, let's see. And if you work this out, this simplifies to 1 over 15, which means that r is equal to 15. So going back to the partial derivative of r with respect to, I forgot that again, r2, we have, it is equal to r squared, so 15 squared, over r sub 2 squared, and r sub 2 is 45 over 45 squared. And that is equal to 1/3 all squared, which is 1 over 9. And there is our final answer, that 1/9 is the partial derivative of r with respect to r2. And that is a very small change in the resistance. R2 leads to a change in R of 1/9. So the partial derivative of r with respect to r sub 2 is 1/9. Now let's look at the second order partial derivatives. If we start with taking the partial derivative of a function f with respect to the variable x, and we take the result of that and take the partial derivative of the result with respect to the partial derivative of x, we're taking the second order partial derivative. And another way to write that is to say we're going to take the second order partial derivative of f with respect to x, and we put a 2, and that does not mean x squared, a 2 right there. Okay, let's move this up, and let's look at another example. Let's say we're starting with the partial derivative of f with respect to y. And if we take the result of that, and from the result we take the partial derivative of the result of the first derivative that we just did, if we take the partial derivative of that with respect to x, this is also a second order partial derivative. And this is equal to the second derivative of f with respect to x and respect to y. And notice here that we're actually going to take the partial derivative first with respect to y and then with respect to x. So let's take that and move that over here. Now, this top one can also be written as the partial derivative, the second derivative, partial second derivative of x this way. And we have two x's, which tells us that we are taking the partial derivative first with respect to x and then with respect to x again. And this bottom one can be written as the partial derivative of first taken with respect to y and then with respect to x. So these are the different ways for expressing second order partial derivatives. In this example, we're looking at f of xy, which is equal to x cosine y plus y times e to the x. Here we're going to find the second order derivative, so that's second order derivative of f, and we're going to find it with respect to different variables. So in our first case, we're going to find the partial derivative of f with respect to x. And that is going to be, well, we're going to have to, when we look at this, our first term is x cosine y. Well, since when we're doing this with respect to x, the cosine y is treated like a constant, and the partial derivative of x is 1. So this is going to be equal to the cosine of y plus, here again, y is a constant. We're treated like a constant. And the derivative of e to the x with respect to x is e to the x. So there is our partial derivative of x with respect to y. So let's move that up there. Now let's find the partial derivative of f with respect to y. Now this time we're going to treat x like it's a constant. And so if x is a constant, well, the cosine of y, the derivative of the cosine of y is the sine of y. So that's going to be x, our constant, times the sine of y plus e to the x is more treated like our constant, and the derivative of y is 1. So this is the partial derivative of f with respect to y. And I did leave out a negative sign there. Let's throw a negative right there because the derivative of the cosine is a negative sign. Okay. So now we want to find the partial derivative, the second partial derivative of f with respect to y and respect to x. Now if we remember how this works, let's move this up. This means that what we're doing is we're first taking the partial derivative of f with respect to x and then with respect to y. And since we already have the partial derivative of f with respect to x here, we just have to take the partial derivative of the cosine of y plus y e to the x with respect to y. And that is, well, the derivative cosine of y with respect to y is the derivative of the cosine's negative sign, so it's a negative sine of y. Of course, the derivative of y is 1, and e to the x is treated like a constant, so e to the x. So there is the partial derivative, the second partial derivative of f with respect to y and x. Now, on the other side here, let's use this to find the partial derivative, or the second partial derivative of f with respect to x and respect to y. And of course here we're going to start by finding the partial derivative of f with respect to y, which we have here. So now we want to find this second partial derivative with respect to x of this, okay? And when we do that, well, we know that we're treating the y like it's a constant, and the partial derivative of x is 1, so it's going to give us a negative sine of y plus, and the partial derivative of e to the x with respect to x is e to the x. Now we're going to find the second partial derivative of f with respect to just x. So that means that we're going to find the partial derivative of this with respect to x, because this is the first partial derivative with respect to x, and now we're going to find the second. So when we do this, the partial derivative of the cosine of y with respect to x is going to be 0 because we treat that like a constant, and then we come here, and the partial derivative of y e to the x with respect to x, y is treated like a constant, and the partial derivative of e to the x with respect to x is e to the x. Okay. And now we're going to come over here and find the partial second derivative of f with respect to y. And that means we're going to find the partial derivative of f with respect to y, and then find the partial derivative of its result with respect to y. Well, here's the result. We already have it. So we have to take the partial derivative of this right-hand side of this equation with respect to y. Well, there's only y in the first term. The second term is treated like a constant, so this is going to give us a 0 when we take the partial derivative with respect to y. So we're just going to work with this one, and our negative x is sort of like a constant coefficient, sort of, and we're going to take the partial derivative of the sine of y with respect to y. So we end up with a negative x times the derivative of the sine of y with respect to y is the cosine of y. And there we have the second partial derivative of f with respect to y. Now, we can take a higher order partial derivative. For example, we can take the partial derivative, the third partial derivative of f first with respect to y, then with respect to y again, and then with respect to x. And another way to write this would be to take the partial derivative first with respect to y, then with respect to y, then with respect to x. Okay, let's move this up, and let's write another one. we could take the partial derivative of f, and this is the fourth partial derivative of f, first with respect to y, then with respect to y again, then with respect to x, then with respect to x again. And this would be written as the partial derivative of x, first with respect to y, then with respect to y, then with respect to x, and then with respect to x again. So hopefully you're seeing the pattern here. So now let's try a problem. Let's say we have a function f of x, y, z, and it's equal to 1 minus 2x y squared z plus x squared y. Let's move that up. So now let's find the partial derivative of f with respect to y. Remember, we're treating with respect to y, so everything else is considered like a constant. And this is going to give us a negative 4 x, y, z plus x squared. And we'll move this one up. I'm going to alternate colors. So now let's find the partial derivative of f, first with respect to y, then with respect to x. So we're going to use the result from above and find its derivative with respect to x, and it's going to give us a negative 4yz plus 2x. We'll move that up. Now let's find the partial derivative of f with respect to y, and then with respect to x, and then with respect to y. So that's going to take the result from the one above and find its partial derivative with respect to y, which is going to be a 4z. And finally, let's find the partial derivative of f, first with respect to y, then with respect to x, then with respect to y, and then with respect to z. And that is going to give us a negative 4. And if we look at the different ways to write these, the partial derivative of f with respect to y can be written this way, and this one, the partial derivative of f with respect to y first, then with respect to x can be written this way. And here we have the partial derivative of f with respect to y first, then with respect to x, and then again with respect to y. And then lastly, this is the partial derivative of f, and I'll set this up this way, with respect to y first, then with respect to x, then with respect to y, and lastly with respect to z. So that sums up our lesson on partial derivatives.